game and what you're going to hear about yesterday. So we're going to hear something about neural operators and where they can play dynamic Stackelberg games.
Yeah. Thank you, Savannah. So, so our talk is about the neural operators to dynamic Stackelberg game. So usually dynamic Stackelberg game is a kind of dynamic games that usually does not admit explicit solutions. So we just try to develop some approximation method using the neural networks to find the approximate solution. So this is our joint work with Guillermo Alvarez and Ibrahim Equin from Michigan and Anastasis Krasil from McMaster. So here's an outline of the talk. At first, we briefly introduce some basic introduction about the dynamic Stackelberg game, and then, and we emphasize that it is not in general not possible to find explicit solutions unless some very special case like the linear quadratic case, right? So, and yeah, of course, in the static case and for the dynamic case, and linear quadratic models are always good to work out. So now we show, but however, we show that there exists a neural operator that can give an approximate Stackelberg equilibrium for the dynamic Stackelberg games. And that is, we also prove that it is an epsilon Stackelberg equilibrium solution. So that is outline of the talk. So here's a basic introduction to the a Stackelberg game that is about the interaction between two players. Usually, one is called leader, the second is called the follower. So each player chooses an individual strategy to minimize the individual cost. So but they don't have the symmetric rules. So because the leader has a dominating power, so that means the follower chooses a best response strategy to the possible strategy of the leader. That means the follower has to be prepared to any strategy of the leader. And then the leader takes into account the response strategy of the follower and then chooses the best optimal strategy for himself. That is how it works. So the pair of the optimal strategy of for the leader, that is called the best optimal strategy, and for the follower, that is called the best response strategy. So this pair is called the Stackelberg equilibrium. So these types of game can be applied in economics and finance. For example, like in oligarchies. For oligarchies, usually when we are studying for example, the commodity producers, like the oil producers, we usually have a small number of producers. We can say two producers. One is the OPEC, and the other one is the rest, right? So that means the OPEC has a dominating power in the market, and the other one has to make strategies following in response to the OPEC's strategies, right? So that means they can play the game. For example, they can play the Bertrand game. That means they can compete by setting the prices. Yeah, but that is not usually true for the oil market. In the oil market, they usually play the Cournot game. That means they choose the quantity of production so as to maximize the individual cost, right? So that is and the other type is a contract design. That means that is a principal agent problem. So here is a basic setting of the Stackelberg game. That dynamic games, that means we have one leader and one follower, and they share the same state, that is xt, and that takes this. We have one leader and one follower, so so they share the same state, and the leader has a control U0. That is also called the strategy. You can also call control. And for the follower, the strategy is U1. They are the variables that enters. Both of them can control the dynamics of the state. So here we just assume a very generic state. We don't assume any special function form. So not work. Froze. Yeah.
Try.
Yeah, it works. Yeah. So now, so no. So for the leader has a cost function like this to be minimized, and no, sorry. Yeah. So the leader has a cost function to be minimized, and the follower has this function form. So they are also generic. That is L1, L0, L1, and G1, G0, G1. They are just generical functions. So here we give the admissible strategies. That means the whole strategy space that the players can take. That means they just take the square integrable processes. So that means we denote them by U0, U1 because they may have different dimension, but they are just square integrable. So we just denote them by H2. Okay, so the leader seeks strategies in a compact subset K0 of the U0. We use a compact subset because later when we are using the neural operator, it acts on compact sets. So that's why here we assume the leader use strategy in compact subsets. So for the follower choose the best response operator that is maps from U0 to U1. So the U0 is a leader's strategy. And then the best response operator that maps into the space of the follower's strategy space. And so that is, we can see the U1 star, that is a RU0, that is a best response. That means it gives a minimal value in comparison with other actions the follower may take. And particularly, we assume the follower take the strategy space. We have some further assumption. That means for each given strategy of the leader, the follower strategy space is just adapted open loop. That depends only on time. And for each U0 for the follower. So here we define the Stackelberg equilibrium. That is a pair of the response strategy and the response strategy of the follower and the optimal strategy of the leader. So for the follower, the response strategy means for each value for each U0 from the leader, the follower takes the best response strategy that minimizes the cost. And then the second condition is for the leader. That means given the response strategy of the follower, the leader choose the optimal U0 star that minimizes the cost. That is how we define the Stackelberg equilibrium. So here are some remarks. So the first one is about the existence of the best response strategy. That means a natural question is whether this the set of response strategy is empty or not. So actually we can see under some very proper convexity conditions for the follower, we can show it is non-empty. So that means it's reasonable to assume it is non-empty. So the second condition is, so because of the first point, then we have that the existence of the Stackelberg equilibrium reduced to find the optimal solution for the J0. Yeah, over the compact subset K0. So here for this paper, our objective is to approximate, because as I mentioned earlier, the U1 star, that is a theoretical Stackelberg equilibrium, that is not always solvable. That means we cannot find it explicitly. So that means we want to try to find an approximate value using a neural operator. So the second is prove the property of the approximate equilibrium. That means we show that the best response strategy, the approximate best response strategy hat U1 from the neural operator can yield an epsilon Stackelberg equilibrium. So here is the basic setting of the attentional neural operators. So that is actually a map from the H2 space to H2 space. That means from the strategy space to strategy space. And it takes this function form. The first part, the EU, that is called the encoder step. That is called the encoder for the attentional neural operator. So that actually maps, that project the input U onto a subspace of the H2. And the second step is is to process the encoded information by the MLP, that is a multi-layer perceptron, that is also called feed-forward neural network. So that is, we use the ReLU activation function. And the final step, that is also called the decoder step, that is apply the softmax function of the output. That means we transform the output by the softmax function, and then takes the average of those parts. So those parts are actually information from the basis of the H2 space. So this part forms a subset of vertices in H2 space. What? D. This D. Little d, right? Oh yeah. So little d is the encoder. It's a dimension of the encoder that is going to be determined, that is going to be trained. Yeah, but we can say that is just a finite subspace. And later we're going to show the D has some contribution to our final result. Thanks. Yeah, so here the multi-layer perceptrons are just the regular neural network settings. So we just use a ReLU activation function. And here is a flow chart of the attentional neural network. So the first step is just to illustrate how it works. So the first step is to project the input U onto a finite dimensional subspace of H2 space. And then the second step is to be transformed by the neural networks. And the third step is a decoder step that gives the output. So the basis coefficients are used to identify the extremal point. So the basis X point contribute to those part. So those are the extremal point, or we said they are the vertices for simplex in a subspace as a subset of H2 space. And the output of the MLP that enters the final step as a softmax function that parameterize the value in the interior of the simplex. Okay, so to proceed, we just give some minimal assumption. So the first assumption is the best response operator of the follower exists. As we mentioned earlier, under very mild convexity conditions, the best response set is always non-empty. And the formal assumption, the one is that the model is, so recall that F sigma are the coefficients of the state dynamics, and the L0, L1, G0, G1 are the running cost and the terminal cost of the two players. So we just assume they have the Lipschitz condition. They satisfy the Lipschitz condition. And for the second assumption, we further assume that the best response map, the theoretical best response map, is Holder continuous. So, and finally, we'll prove that it turns out to be Holder continuous with parameter a half, right? Yeah. Okay, so the first question is is about the existence of the approximation operator. That means, can neural operators approximately play the Stackelberg game? That means, can it give some approximate solution to the best response operator? So here's the first part of the work. That is, for each compact subset, there exists a neural operator hat U1. That is the N0 is a neural operator we defined earlier. So that means it satisfies this condition. That means this is a theoretical best response operator that is unknown, but we want to know that. So we approximated by the neural operator, approximated by this. So we showed the existence of hat U1 such that they satisfy any desired accuracy. That is the first step. So yeah, okay. So the second step is once we have the existence of the hat U1, how does it contribute to the approximate Stackelberg equilibrium? So here's the property. That means there exists a U0 in the compact space for the compact strategy space for the leader. And there is a D dimension D. That is why the D is important. That means the dimension of D is to be determined. So there is a D such that this pair, that is hat U0 D, that is a projection of this U0 onto a subspace, right? So that means this pair is an epsilon Stackelberg equilibrium. That means this one. That means the distance of the value of the leader under the hat U0 D and under the approximate best response hat U1, the distance to the theoretical minimum value is less than epsilon. That is why we call it the epsilon Stackelberg equilibrium. Yeah, that means we can yeah. So the second question is how to train a neural operator. That means how to find it out, right? How to determine it. The first theorem just shows it exists. So the second question is how to train it. So here is a natural idea. That means minimize the mean value of J0. That means we are minimizing the mean value. So that means the mean value, this mean value depends on hat U1. That means depends on the parameter values of the neural operator. We need to train it by minimizing this mean value to determine the parameter values of the neural operator. That is a natural idea. But the problem is it's not implementable in practice. Why? That is because the K0 is infinite dimensional. So that means theoretically it's okay, but if you want to write some algorithm to do it, it's not implementable. So here we have instead we train it under a subspace that is for U0 in the compact set. We train it under the hat U0 D that is projected onto the finite dimensional subspace. So here is the theorem that can support the trainability of the neural operator. So okay, let's take a look at how the theorem says. So it says if hat U1 satisfy this, then this hold. So this actually gives the necessary condition for the optimality of the hat U1. That means because if they satisfy this, if they satisfy the first line, then we have the second line. But the thing is, we want to find hat U1 to achieve the first line. So that is but the thing is, we can take a heuristic approach. That means we just use this necessary condition to find out the optimal, to find out the parameters for hat U1 that minimize that minimize this. It's just like we use the necessary condition to minimize, to do the optimization. That is something like that. So that means the key point is to minimize this as soon as possible, because the minimum value of this must be this. Yeah, so okay, so to prove, so just now we saw two primary results using the about the existence and trainability of neural operators for the approximation solutions. So here we have to prove the two theorems, we need some intermediate steps. So the first step is about the regularity, the Holder continuity of the theoretical U1 star. So, but we can prove that under our assumptions. That means just under the Lipschitz conditions, we can prove this. And the second is about the second is a key part, that is about the universal approximation. That means for any target function, or we say this is a target map, so it can be approximated by an attentional neural operator. So that means it can be approximated at any desired accuracy. So here in our application, we just take the target, function to be the theoretical best response operator. Okay, the third step is also about the stability of the value function for the major player, for the leader. So that means it should have this regularity, this stability. Yeah. This we have also proved this. Okay, so here is about the conclusion of what we have done. So it's almost done. So that means the first is we proved the existence of a HAT-U1. That is a neural operator that can approximate the best response. And the second part is we provide a heuristic method to train a neural operator by minimizing the mean value of J0. And then the third one is we find the epsilon Stackelberg equilibrium with the approximate best response HAT-U1. That is our main result we get. That's all. Thank you.
Thank you very much. Are there questions in the audience?